All right. So, okay, good. So today we'll talk about atomic absorption. More than half of you already took the lab, so this is going to be a nice, easy theory review for you. Others, this would be an introduction to the lab on Wednesday. So atomic spectroscopy deals with the quantification of elements, so in atomic form. So what type of energy would be associated with this kind of absorption? Is it electronic? Is it vibrational? Is it rotation? Electronic. Okay, so electronic energy is associated with the absorption of light and emission of light from an atom. And there are 4 different types of atomic absorption and emission together. So there's flame atomic absorption, which what you did in the lab or will you do on Wednesday. There is the electrothermal atomic absorption. We'll talk about that. You did not do this in lab. You will not do it in lab. Flame emission, and here you measure the emission of light using flame as an excitation as well as an atomization source. And inductively coupled plasma atomic emission spectroscopy. So these are the different forms of atomic spectroscopy. And they're mostly used in food analysis to determine mineral content for nutritional purposes. Mainly, for example, calcium and iron would be for the nutrition labeling. Other is for determining essential minerals. Sometimes you see on a cereal box a list of minerals that's been added to your mix, so you have to quantify them and therefore be able to list them. And then, of course, we are interested in determining if you have any heavy metal or residue of heavy metal which are toxic, and so it would be means to determine toxic elements as well. So not every atom form is quantifiable by atomic absorption. Only the metallic atoms. So these are highlighted in red. Is often can be analyzed by atomic absorption. So, like I said, we are interested in essential nutrient quantification, such as calcium, phosphorus, sodium, potassium, etc. And then the toxic elements, we are interested in quantifying lead, mercury, cadmium, and nickel. The USDA database has a good database for specific elements, not every single element. Database meaning the amount of different minerals in different foods. So there is a complete or sort of complete database for certain elements, but not everything. These are the table 24. One is in your textbook as a reference, FYI. So again, a reminder, in atomic absorption, we are measuring electronic energy, or it's the absorption of electronic energy. So basically, a photon of light hits an electron transitions into a higher shell, and that would be an excited state, and then when it releases its energy, part of it is heat, part of it is emitted as a photon of light, and that would be measuring emission. So all of the mineral elements can fluoresce or can emit light. So sometimes we measure absorption, sometimes we measure emission, depending on the instrument that we have. And the absorption and emission is basically measured in the atomic state, where the atom is neutral, not necessarily ionized, and it is in the volatile state or the gaseous state. So every element has its own unique spectra, meaning every element absorbs maximum at a particular wavelength and also emit radiation at a particular wavelength. So for example, this is element A, it absorbs light at about 340 nanometer and emits radiation maximum at about 520 or 530 nanometer. Again, emission of light is always at the larger wavelength because part of the energy is emitted as heat, dissipated as heat, and the remaining energy is dissipated as light, and that's why it has longer wavelength, given that longer wavelengths are associated with smaller energy. So what I want to show you here is that, again, absorption occurs when the element goes from a ground state to an excited state. But you see here, there is the electronic transition, and there is the rotational and vibrational energy transitions over it. But in atomic absorption or emission, you don't have these levels because you don't have vibrational or rotational. You only have transitions from ground level to another excited state to another excited state based on the allowable energy transition at particular wavelength. So there is no, you don't see rotational and vibrational energy in the energy transition of an atomic, of an atom, basically. So, like some of you went over this in lab, basically the sample will be in a liquid form, and you have your elements dissolved in it, and we'll talk about how you do that later on, sample preparation. But you have your sample, which is in a liquid form, and you have your element dissolved. And the sample is aspirated into the unit, or the atomic absorption, and transformed into fine mist by a nebulizer. So the liquid is sucked up by, and then after that it gets to a nebulizer, which transforms the liquid into a mist, and that mist hits the flame or the plasma. And the flame or the plasma is your sample cuvette, basically. Instead of putting a sample in a tube or a cuvette to measure absorbance, your sample compartment would be your flame or plasma. And from there, once your mist hits the flame or the plasma, the vaporization occurs. Your solvent evaporates, and also your atoms that are in a molecule form, bonds are broken, and the atom becomes in gaseous phase. So you have a molecule here, and then these bonds are broken, and then you have atoms in a neutral form that's not ionized. So basically solution, dissolution, you have your minerals. Usually the minerals in your solution is not as such. It's either, for example, potassium sulfate, or you have ferric chloride, or you have sodium chloride. So you have it as a molecule, and in solution will be interacting with the water. And then when it hits the flame, you have dissolution and evaporation of the solvent. And then you have the solid, which is your sodium chloride, for example. And then your this becomes vaporized by the flame. You have the gas, and then you get this molecule broken down into atoms. And you have, at this stage, you have a source of light where it gets excited from ground state to an excited state. But one thing we want to avoid is having the atom transfer into an ion. That happens if the flame is too hot. If the flame is too hot, then your atoms become ionized. That's why those of you that did the lab, the flame was, or Cindy showed you how the flame gets optimized to maximize atomization and avoid ionization. If you haven't done the lab yet, you'll do it on Wednesday. But yeah.
So what happens to X?
The X remains, it becomes another atom, but it's not detected by like chloride. We do not detect
Okay, so
it.
just can't detect it.
It's not, yeah. So the source of excitation in atomic absorption is a lab. And the lamp that is mostly used for the hollow cathode lamp is called hollow cathode because you have a compartment that is empty and filled with argon gas or neon. And then you have a cathode made up of the element, the metallic form of the element that you are trying to detect. So if you're detecting iron, you have a cathode made up of the iron metal, calcium, zinc, etc., sodium. You'll have the cathode made up of that particular element in a metallic form, and then you have the anode. And then when the electric current hits, so the cathode gets excited, or the metal gets excited and emits radiation in the spectra specific for that element. So only the light within the spectra that the element can absorb or emit radiation. So often, or in most cases, you need a specific lamp for every element. So in the lab, you either have analyzed already the calcium or iron and you use two different lamps, or you're going to do that on Wednesday. So you will have two separate labs. Each lab will have a cathode made up either of calcium or iron. Sometimes you have a lab that have multiple cathodes in them, but generally it's 2 to 4 maximum. You don't have a lot of different elements within one lab. So therefore, it is important to change the lamp based on the element that you are detecting. Otherwise, you won't get the spectrum for the absorption that is specific for that element. There is another type of lamps, less commonly used, or at least it's not compatible with the AA we have in the lab. So this kind of lamp doesn't have electrodes in it. It does have the element of interest for the emission of the specific spectrum, but the excitation occurs by the discharge produced by radio frequency generated by a coil. So it's just a different mechanism of excitation than the other one. It's still also filled with inert gas such as argon. The same as HCl stands for hollow cathode lamp, not the HCl acid. It's commonly used for those elements that are more volatile elements, but the other lamps can be used for general purposes as well. This is actually the older unit that we had in the lab. I should take a picture of our newer AA, but basically it's a similar unit but newer. You attach to the unit acetylene for fuel and air or nitrous oxide as a source of oxygen for the generation of the flame. And then here you have a tube, a very tiny capillary tube. This is a newer model, but again, not the one that we have. I should get a picture of that. So you have a small tiny capillary tube that will be placed in your sample, and that tube will aspirate your sample into the nebulizer. So it goes in there, and the sample nebulizer would convert the liquid, a small portion of the liquid. Most of the liquid is going to go into this large tube here going to the waste. You only need a very small amount of your sample that get nebulized and converted to mist, which goes into this compartment. This will light up into a flame, and the sample would be brought up to the flame, and then that's where desolvation occurs and evaporation of your element occur. And in the hot flame can have about 2000 degrees Celsius, the temperature, around that estimate, and that's when your molecules break into atoms, become volatile. So this is the drawing of that. So here's your flame when it's ignited. So here's your capillary tube where your sample is, sucking up some of the sample into the flame. And then you have the lamp, which is when the current is applied, You get spectrum in the specific element of the cathode, and that's your incident beam, and your sample is in the flame, will absorb radiation, and some of them will absorb or emit radiation. That's why you have a monochromator should be in here, which would select for the light at a specific wavelength where you're measuring absorption, because there will be other light emitted as well as the light that is passing through. So there should be a filtering before reaching the UV detector. And once transmittance is measured, is converted to absorption, and then absorption is used to quantify the concentration, which is the Beer's law is applied. Absorption equal absorptivity times the length. In this case is the length of your flame, and then the concentration. So here's a more detailed schematic. So the hollow cathode light lamp will emit radiation that is specific for the element, and we normally measure at the absorbance at which you have, or at the wavelength at which you have maximum absorbance. So you select for that wavelength, and then you will have some of the light is absorbed, so what gets measured, the transmitted light will be obviously less than the incident beam, and that's what gets measured. And like I said, there is a monochromator after the flame to just remove any emitted radiation and filter it out, and just allow for the detection at the wavelength specific for that element, which is maximum absorption at a specific wavelength. And usually the one that we have in the lab, the detector, is a photomultiplier tube detector. If you remember from last lecture, in here you have an amplification of the electrons within conversion of when the light hits, an electron is generated, and then there's an amplification of the electrons, and then you get an amplified signal, enhanced detection. And then you get an electrical signal converted to an absorption that is detected by your software. Another type of atomic spectroscopy is, instead of using a flame, there is a graphite furnace, or a tube. So the sample compartment, instead of it being a flame, it would be a unit, a graphite surface platform, where it heats up between 2,000 to 3,000 degrees Celsius. So here you would need just a little bit of sample. If in your lab you'll notice that you'll prepare about 10 milliliter of sample, and some of it get aspirated as detection is made. Here maybe a few drops of the sample on the surface here would be enough. So if you have only a little bit of sample, just not a lot of volume, so this would be great. Also here you have very good threshold, much lower threshold, higher sensitivity than the flame. However, the difference is it is more expensive and lower sample throughput, because in your atomic absorption with the flame, you put your capillary tube in one sample, you take it out and you put another sample, and you keep going. So it has very high throughput. Here you have to make sure that you put a sample every time, and it's going to be hot, so you have to be careful in handling how you put the sample in. So it is difficult to operate because you'll be dealing with really hot surface, and you're trying to put your sample in there every time. So there are advantages and disadvantages associated with that. Okay? You can interrupt me for questions if you have any. Okay, atomic emission or flame. You have two types of atomic emission spectroscopy. One is flame emission. In this case, your flame is not only used to atomize, it also excites. So the temperature of the flame causes atomization as well as excitation. So but it's only used for those elements that have low excitation energy. For example, sodium and potassium, they're often analyzed using flame emission. Because while low excitation, that means the flame is sufficient in getting them excited for emitting radiation. The other type of emission spectroscopy is the ICP, which is the inductively coupled plasma atomic emission spectroscopy. In this case, your argon gas gets ionized, and the ionization of the gas along with the heat generated, along with radio frequency power applied to the argon gas, you get a very hot plasma generated. So when, I'll show that in the next slide, but meanwhile the plasma is the source of atomization and excitation. So here there's no lamp, you don't need a lamp. The plasma generated will break the molecules into atoms and will be exciting the atoms, and then the atoms will emit radiation, and that radiation will be detected. Temperature can be really high for effective atomization. However, the advantage of the plasma is you don't get ionization of your sample. So even though it's at a high temperature, there is no ionization occurring. So your atoms remain in a neutral atom form. Why is that? Because the argon gas has a lot of electrons, and it has a positive ions and free electrons, suppressing the ionization of your atoms. So presence of ionized argon prevents or suppresses ionization of your atoms at this high temperature. So same thing, you need to have a nebulizer. You'll have your sample, and then you have a capillary tube sucking up the sample into a nebulizer that converts your samples into aerosol or small particles, and the particles travel into the plasma that is generated by the ionized argon and the radio frequency energy. So in the plasma, your atoms get excited and then they emit radiation. The radiation passes through to your detector. In there you have a grating system, because you have multiple elements, all are emitting radiation in different spectra. So what happens is that you will have to separate those wavelengths into separate wavelengths, and they get projected into a series of photomultiplier detectors. So if you can see here, this one unit has several photomultiplier detectors, not just one, but several. So you have here about 7 different ones. So you can, in this example, you can detect 7 elements at the same time. You don't, so the nice thing about this, there's no lamps, you don't have to change the lamps. The plasma will allow every element to emit radiation, and you can detect as many as you have photomultiplier tubes simultaneously. So you can do simultaneously if you have multiple. Sometimes you can do sequential. That means you would have one photomultiplier tube, and then you will sequentially change the selection of the wavelength, and then you will read emission at different wavelengths. So here's just a diagram showing what happens. The ignition spark ionizes your argon gas, and then the coil here gets radio frequency that will collide with the ionized gas and heat it up. So it will collide with the electrons present in the ionized heats it up to high temperature. And this is just different temperature at different points in the plasma. So it's just a diagram, and here is just another diagram just showing you that the plasma can be either horizontal, a vertical or horizontal to the spectrophotometer, the detector. And in this, you have higher sensitivity and lower threshold because you would have more focused emission. The setup than this setup. So that's, it's like here it says 5 to 10 times higher sensitivity, basically. What? Jammed. Oh, there we go. Did it move? Okay. What? I wanted to see how many times it moved. What? Oh. Why? Escape. Jammed. Huh? I don't know why. It's processing. Oh no.
Is there a difference in cost to have it set up as a radial plasma versus axial? Is there a reason?
I don't know if there is a difference in cost. Good question. I don't know.
Oh.
What happened is just decided to go out of presentation mode. Oh, that's right. I hit escape, but it's a lot delayed the response. So what was your question?
Well, I was just commenting on that. The axial has to almost be more expensive because with that flame's directed at the spectrometer.
Yeah.
It's going to need a heat shield on it. It's also going to need to be a beefier device. So I would
There
assume
you
that's
go.
going to be a much more expensive piece of equipment.
Good. There you go. You got Andy to answer that. Huh?
Did you explain what the matrix interference is?
Yeah, I was going to talk about matrix interference later on.
Okay.
It's coming. But the matrix interference is that whatever you have in your solution that is being aspirated with your elements into the flame. So you will have more interferences here because if you have that direct connection to the detector, where here you don't have as much. Okay?
So is that tied with what you said about having a lower threshold?
Yes, because you have, yeah, exactly. So you have lower threshold, but at the same time, if you have a lot of complex stuff coming in, then you will have higher matrix interference. Everything has advantages and disadvantages. Okay, so I was saying that you either have a sequential or simultaneous detection. In a sequential detection, you will have one photomultiplier tube detector, and you just sequentially change the monochromator to select certain wavelength. Simultaneous, you will have a certain number, and some instrument comes with a set number of photomultiplier tubes, and the more expensive it is, the more photomultiplier tubes you have. Or the more photomultiplier tubes you have, the more expensive is your instrument. But the best one of all to have, which is more expensive, is the Ishel spectrometer, which in this case it will have two types of detectors, the charge injection devices and the charge coupled devices. I'm not going to go into the physics of those, but basically what they do is they allow detection simultaneously of multiple elements. So you have two types of gratings in this, two types of light diffraction. I would say you have a prism. So what comes from the plasma goes in, the emitted radiation goes in, projected to a mirror, the mirror projected to a prism, and from the prism get projected to a grating, and all these different wavelengths reaches the detector simultaneously. The detector will be made up of a lot of pixels. Pixels will contain and generate and store energy when they are hit by light, and they will convert that energy to electrical signal. And they will produce spectra for you. And so you will simultaneously be able to detect multiple elements in one run. So in order for you to get your mineral analysis, you have to get your sample in a liquid form. And that requires that your minerals can get released from your carbon matter. In order to release them from the carbon matter, you need to combust your sample. And you do that either by dry ashing, putting it in a muffled furnace at high temperature, 450 to 550 degrees C, and all of your organic matter burns off, and what you end up with is your elements or your salt. I would say salt because they are in molecular form. And then you dissolve them in acid and you dilute to a certain concentration so that it fits with your standard curve. Wet ashing is also combusting your carbon matter but using corrosive acid. So you digest with an acid rather than you burn with heat. We'll talk more about dry ashing and wet ashing when we cover the ash chapter. But here it's just basically you want to remember that you want to get rid of your carbon matter so that you release your mineral, that you can solubilize it and eject it in your atomic absorption or emission. Direct injection of a sample, this really happens only if you have a liquid sample that has very low concentration of different interfering material, like for example oil. You can directly inject oil sample without having to do pre-ashing to it. Okay, I will stop here for now, continue on Wednesday. A few more slides before going into IR. All right.